Hello there. Recall that in the last video, we discussed the formal definition of limits. So we define the limit of f of x as x approaches a is L if and only if, for all epsilon greater than 0, there exists delta positive such that if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. To understand how this works, let's try out some examples. So in the first example, our goal is to prove that the limit of 2x minus 3 as x approaches 2 is equal to 1 by the formal definition of limits. Before we start, feel free to pause the video so that you may try this one first on your own. Okay, good. So let's start. So at first, doing and applying the formal definition, it's quite tricky since it's very structured and there's a certain step that we need to follow. From the definition, we start by, so the definition states that for all epsilon greater than 0, so we let epsilon be greater than 0. After that, the definition mentions that there exists delta positive, so we choose or take a delta, which we still don't know, which we will choose, but we leave this one as a blank so that we can supply this one on, or this one later on. After that, we mention that the absolute value of x minus 2 is between 0 and delta. So in this case, we have x minus 2. So this is the x minus a part of the definition since x approaches 2 out here. So we have to be this one. Such that if this is the case, then we have 2x minus 3 minus 1, or this one is the absolute value of f of x minus L is less than epsilon. So our goal is to make this one less than epsilon. And we'll do that by applying some steps, since we can't really immediately show that this one is less than epsilon. But this is our goal, so keep that in mind. So again, we let epsilon be greater than 0, take delta to be something that we'll be supplying on later, and then if this is the case, then this one must be less than epsilon. So let's start by simplifying this. So we have absolute value of 2x minus 4. Then take note out here that we can factor out the 2 out here. Oops, this must be 2. And then we can bring out the 2 outside of the absolute value. So we'll have this. Now this might seem to be a dead end since this one is already in its simplest form. But take note that at this part, the dead end part, we can use the assumption that we are given, which is this one. Or specifically this part out here. So we know that the absolute value of x minus 2 is less than delta. This means that this part out here is less than delta. So this whole out here is less than 2 times delta. Now again, keep in mind that our goal is to make this part, the absolute value of f of x minus L, to be less than epsilon. So what delta should we choose such that this one is less than epsilon? Well, we can choose delta to be epsilon over 2. Since if it is epsilon over 2, then epsilon over 2 times 2, so the 2 would cancel out and we'll be left with epsilon, which is what we want. Take note that epsilon over 2 out here is greater than 0 since we know that epsilon is greater than 0. So if we divide 2 in this case, this will give us epsilon over 2 to be greater than 0, which is still positive, so it matches what we want. So replacing delta here with epsilon over 2 will have 2 times epsilon over 2, dividing the 2's, and we'll be left with epsilon. So we have shown that for all epsilon greater than 0, there exists delta, which is equal to epsilon over 2, which is positive, such that if absolute value of x minus 2 is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. So this ends our proof. And so that is how we apply the formal definition of limits. Let's try out the next example. So in here we are tasked to prove that the limit of 7 minus 5x as x approaches -1 is equal to 12. So again, feel free to pause the video so that you may try this one first on your own. Okay, good. So let us start. Again, the process is similar to the first example. We start by letting epsilon be greater than 0, and we take delta to be something that we'll be supplying on later. So we leave this one as a blank, such that if the absolute value of x minus -1 in this case, so -1 out here, simplifying this, so we'll have this is equal to absolute value of x plus 1 is between 0 and delta, then we have 7 minus 5x minus 12, or the f of x minus L is less than epsilon up after some series of steps. So again, this is our goal. So to start, we first simplify this expression inside. So we have 7 minus 12, that will give us -5. So we have the absolute value of -5x minus 5. Take note that we can factor out -5 out here. So we have this. And if we bring this one out of the absolute value, this one becomes positive now, since that is how absolute values work. So we have 5 times absolute value of x plus 1. Now at this part, the part that seems to be a dead end, again we can use this condition. So we have the absolute value of x plus 1 is less than delta. So if this is less than delta, this means that, oops, this looks like 8. Let's fix that one. There. So if this one is less than delta, then this whole out here is less than 5 times delta. And again, at this part, we can now choose what delta we want to make this one less than epsilon. This one less than epsilon. So clearly we can choose delta to be epsilon over 5. Again, we know that this one is greater than 0 since we have epsilon to be greater than 0. So if this is greater than 0, it follows that the whole is greater than 0. So replacing delta here with epsilon over 5, we have this. And then we can divide the 5's out here, so we'll be left with epsilon. And so we have shown that for all epsilon greater than 0, there exists delta, which is equal to epsilon over 5, which is positive, such that if absolute value of x plus 1 is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. So this ends our proof. We have shown that the limit of 7 minus 5x as x approaches -1 is indeed 12 by its formal definition. So I hope you got that one correctly. Let's now move on to the last example. So this one now is quite trickier than the first two, since we have the presence of square. But again, feel free to pause the video so that you may try this one first on your own. Okay, good. So let's try this one out. So to start this one, we do the same process in the first two examples. So we let epsilon be greater than 0 and we take delta to be something that we'll be supplying on later. So if absolute value of x minus 3 is less than delta, my mistake, there should be a, this one. So just take note of that one. Apologies for that mistake. Then we know that absolute value of x squared minus 9, or the f of x minus L, is less than epsilon. So this is what we want to show. So to start, this might seem to be a dead end since x squared minus 9 out here is in its simplest form. Might look like it is already in its simplest form, but take note that by difference of two squares. So take note that if we have a squared minus b squared, this one is equal to a minus b times a plus b. So applying this one in this expression, this one is equal to absolute value of x minus 3 times x plus 3. And by property of absolute value, we can split this one. So we have this. Absolute value of x minus 3 times absolute value of x plus 3. In here, we can use again this bound out here. So we know that this one is less than delta. This means that this whole out here is less than delta times absolute value of x plus 3. Our problem this time is the absolute value of x plus 3. We need to find an upper bound for this one. Well, take note that the delta out here is arbitrary, so we can choose it to be sufficiently large or sufficiently small. And I think it wouldn't harm us to assume that this one is less than or equal to 1, since we're dealing here with values close to x values close to 3. So this is like their distance. And we're dealing with very, very close values, like almost 0. So we can probably assume this one. Well, actually, you can make it large if you want, but you'll see later on how we will use this one in answering this problem. So let's assume this one. So we have absolute value of x minus 3 is less than delta is less than or equal to 1. Again, we have a choice to make this sufficiently large or sufficiently small. So given this, so we know that absolute value of x minus 3 is less than or equal to 1. It's less than, since this one. So this means that by absolute value inequalities, if we have this form, we split this into x minus 3 is between -1 and 1. And again, our goal is to find an upper bound for x plus 3. So we add 6 in here, all sides, to get x plus 3 is between 5 and 7. In here, take note that 5 is greater than -7. So if we focus on this part, and this part, then we know that the absolute value of x plus 3 is bounded by 7. So we'll use this one in answering this one. So we know that this part out here, given this, is less than 7. So we have found a upper bound for it, but take note, so don't forget that we set delta to be less than or equal to 1. So let's move this one first. So we have this. Now in here, the next step is to choose what delta we want in here. The delta that we would be choosing is the minimum or the lower value between the two numbers 1 and epsilon over 7. And you'll see why later on. Well, actually now, I'll try to explain it, how it works. So we need to take note that there's a possibility that 1 is a smaller value out here, since we set delta to be less than or equal to 1. So there's a possibility that delta is already equal to 1, or if not, then it's probably epsilon over 7 that is equal to delta. But in either cases, you'll see that the outcome would still be the same. So suppose that 1 is less than epsilon over 7. 1 is less than epsilon over 7. So we choose delta to be equal to 1 out here. So we have, this one will be, f of x minus L is less than 7 times 1, which is equal to 7. But we know that 1 is less than epsilon over 7. So this one will be equal to 7 times epsilon over 7. So cancel this one and we'll have this. So we'll still obtain what we want for this case. But take note out here that we have here 7 times delta to be less than epsilon. Now, if epsilon over 7 is the lower value between the two, then we have epsilon over 7 to be less than 1. And so we immediately choose delta to be equal to this. So we have 7 delta, which is equal to 7 times epsilon over 7. So this, and we'll get epsilon. So we'll still end up with what we want. But this time, 7 times delta is equal to epsilon. That's why, by taking this value of delta, this one out here becomes less than or equal to epsilon. But take note that this is what we want still, since we have shown that for all epsilon greater than 0, there exists delta, which is equal to the minimum value between 1 and epsilon over 7, or between these two numbers, which we know to be positive since 1 is greater than 0 and epsilon is greater than 0, so epsilon over 7 is greater than 0, such that if absolute value of x minus 3 is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. So this one completes our proof. So as you can see in this example, it's quite trickier to take delta since we have the absolute value of x plus 3 out here, which we need to take bounds on. Since we only know that this one is bounded by delta, but we don't know what for absolute value of x plus 3. So I hope you got this one correctly. To end this, here are some exercises that you can work on. So we have the limit of 3x minus 5 as x approaches 0 is equal to negative 5. The limit of 2 minus x squared as x approaches 1 is 1. And the limit of 5 minus 3x plus x squared as x approaches negative 1 is equal to 9. So your goal is to prove these examples by the formal definition of limits. So in the first example, this is just parallel to our first two examples. And for the last two, this one is parallel to the third example that we have. So this two out here is quite harder, but you can do it since you just follow the steps that we have. So I hope you understand the process and I hope you enjoyed and learned a lot from this video. Feel free to comment down below if you have solutions and answers for these exercises, as well as if there are some confusion in your part on the solution or the proofs that I made in the examples. So yeah, that's it, and that is all for this video.